The setup for problem 1.31 is to imagine some helium in a cylinder with an initial volume of 1 liter and an initial pressure of 1 atm. Somehow, the helium is made to expand to a final volume of 3 liters in such a way that its pressure rises in direct proportion to its volume. Part A asks us to sketch a graph of pressure versus volume for this process. To begin, we know that the pressure of the helium gas is directly proportional to its volume, so we can write it as pressure is equal to some constant K times V. Now, what we know is that the initial pressure must be P initial equals KV initial, and the final pressure must be P final equals KV final. What we then do is divide the P final equation by the P initial equation. Now we can move over P initial, cancel out the K's, and we now have an equation for P final. We can now plug in our conditions that it's initially at 1 liter and 1 atmosphere, and its final is 3 liters. This tells us that the final pressure is 3 atmospheres. Finally, we get the plot seen here, where it is just a linear graph from 1, 1 to 3, 3. Part B asks us to calculate the work done on the gas during this process, assuming that there are no other types of work being done. To begin, we'll express the amount of work done on the gas during this process as work equals negative integral of pressure times the derivative of volume from V initial to V final. We have a negative here since this is the work being done on the gas. Now we will substitute kV for P as we did in part A. We can now pull out the K and solve this integral. The result will be negative K times V final squared minus V initial squared over 2. Now we have to take our initial volume, which was 1 liter, and convert it into meters cubed. We will also take our final volume, which was 3 liters, and convert it into meters cubed, and we will get that those are 0.001 meters cubed and 0.003 meters cubed, respectively. Then we have to convert the units of initial pressure from atmospheres to newtons per meter squared. That should give us 1.013 times 10 to the 5th newtons per meter squared. And our P final should be 3.039 times 10 to the 5th newtons per meter squared. Now we can use equation 1 and solve for the value of K, which is P initial over V initial. If we solve that using our new values for P initial and V initial, we should get that K is 1.013 times 10 to the 8th newtons per meter to the 5th power. If we plug all of these values we just solved for back into our original work equation, we should get that work is negative 405.2 joules. Part C asks you to calculate the change in the helium's energy content during this process. We will assume that helium has 3 degrees of freedom, and so we can write its thermal energy as 3/2 nkt, where n is the number of particles, k is the Boltzmann constant, and T is the temperature. Using the ideal gas law PV equals nkt, we can replace the nkt with PV. Then we can look in the change in this thermal energy by looking at U final minus U initial, where U final is 3/2 P final V final, and U initial is 3/2 P initial V initial. And we solved for P final, V final, P initial, and V initial in part B. So plugging those in, we should get that the change in thermal energy is 1215.6 joules. Part D asks us to calculate the amount of heat added to or removed from the helium during this process. We know that the internal energy must be equal to the heat added plus the work done, or delta U equals Q plus W, where Q is the heat added and W is the amount of work done. We can rewrite this equation as Q equals delta U minus W, where we put in our 1215.6 for delta U and our negative 405 for W, and this gives us 1620.8 joules. The positive sign of the heat shows that the heat is added to the system. Part D asks us to describe what you might do to cause the pressure to rise as the helium expands. In order to get the pressure of the helium to rise during the expansion, you would need to add heat. As the heat is supplied, the kinetic energy of the gas increases, and so the kinetic energy of each of the gas molecules would also increase, creating more pressure within the cylinder.